Let's review the Claisen condensation and see how it can be applied towards synthesis problems. Shown here is an example of a Claisen condensation. We have an ester and we're treating it with a base. Notice that the base, because it is an ethyl ester, I'm using sodium ethoxide, so we always want to make sure that the base is going to match the ester we're using. That's to avoid any hydrolysis products or transesterification products. In other words, this ethoxide can act as a nucleophile, and if it added into the carbonyl, that would be okay because elimination of the ethoxy group would be kind of an invisible reaction. I'd be replacing ethoxy with ethoxy. So anyway, what's happening here is we are going to react two equivalents of the ester, one with the other, and the first equivalent is going to act as our nucleophile at the alpha carbon, and the second equivalent is going to act as our electrophile at the carbonyl carbon. And so if this looks at all familiar, you might be thinking that you've seen a reaction like this before. It's very much like the aldol reaction. The aldol uses aldehydes and ketones, and the Claisen uses an ester instead. So here's our new carbon-carbon bond that was formed. And the product we're going to get is a beta keto ester. So let's take a look at the mechanism for the Claisen condensation. Our reaction is going to start with a deprotonation with our ethoxide base. So we're going to make the enolate. You can make an enolate of an ester just like you can make the enolate of an aldehyde or a ketone. And that is going to be our nucleophile. And the electrophile we have is the neutral undeprotonated ester that's still around. So again, notice we have an equilibrium situation here. Just a small amount of this ester is going to be converted to its enolate. So the rest of the ester remains, and so we have both the nucleophilic and electrophilic components present. So we're going to attack the carbonyl with the enolate. I like to redraw the enolate kind of standing upright. And there's our new carbon-carbon bond. And now what do we still have at that carbon? We have, so we're looking at this carbon now, and we want to still have these three groups on here. So we still have the ethyl group and the ethoxy group and an O-. So up till now, this is exactly what we expect for what happened with the aldol reaction. But what's unique here is instead of just doing a workup where we would protonate to get the beta hydroxy product, this product is a very special intermediate. It's described as a charged tetrahedral intermediate, or a CTI for short. And what's special about a CTI, what makes it a CTI is we have a tetrahedral carbon here, and we have at least two groups with lone pairs. And one of those groups is charged. That's why we call it a charged tetrahedral intermediate. And what's going to happen is this is going to collapse where one group with the lone pair is going to push the other group out. So I'm going to kick out a ethoxy molecule here, ethoxide group. And I'm going to reform the carbonyl. So as usual, when a nucleophile attacks an ester, we have a leaving group here. So we get a two-step procedure where we do addition into the carbonyl and then elimination of our leaving group. So the original carbonyl is still intact. We got an acyl substitution where the nucleophile coming in was this enolate. And it kind of looks like we're done here because that, in fact, is the product that we get. But under these reaction conditions, we actually don't stop because this proton is now between two carbonyls. We call this, this is a very acidic proton. We could describe this as an active proton because it has two electron withdrawing groups next to it. And so in these basic conditions, we very much will deprotonate this product as it's formed. In fact, this is the driving force of the reaction, and in the absence of this proton, in the absence of an acidic proton being present, the Claisen reaction doesn't occur. The Claisen reaction would just be reversible. So this is actually the final product. Anion is final product. What we have here is we could describe this as a stabilized enolate. All enolates have resonance stabilization, but this one has extra resonance stabilization because it could delocalize over this carbonyl and this carbonyl. So very, very stable enolate is our final product. And that's why we have this last step here. Notice we have our H3O plus workup. We always have to include that in our Claisen reaction because that's going to be our final step of our mechanism, is going to be protonation to go back to our neutral product. So step 2, we'll just describe this as a workup, an acidic workup, where we're going to have some water present, some acid present, where we can go back to our neutral product. So there's our beta keto ester as our final product. So reviewing this reaction, the Claisen condensation reaction, it's going to help us when we now have a target molecule that has a 1,3 dicarbonyl pattern. How is that going to affect our retrosynthesis? So let's take a look at this product from a retrosynthetic point of view. If this is my target molecule, what I'm going to do, as usual, is I'm going to focus in on the alpha carbon, and I'm going to make a disconnection at the alpha carbon. So the alpha carbon was my nucleophile as the enolate, which means the other carbon it's going to react with was my electrophile. Okay, now the difference here compared to an aldol disconnection is that we still have a carbonyl. And how do we still have a carbonyl? We still have a carbonyl because there must have been some kind of leaving group attached to the electrophile, so that after the enolate attacked, the carbonyl was reformed. So here's our alpha carbon nucleophile and our carbonyl carbon electrophile. And typically the leaving group we use here would be an ester. The ethyl ester is very commonly used because it's such a good, it's commercially available typically. That's the most common one to encounter. And so this disconnection would lead back to a self-aldol condensation.